Hello, welcome to another module in this massive open online course. So, we are looking at the concept of autocorrelation of a signal xt, correct. So, we are looking at the autocorrelation of a signal the autocorrelation of a signal xt, and this is R11 of tau, or autocorrelation x1 t is R11 of tau integral minus infinity to infinity x t into x conjugate t minus tau dt. Now, since there is only one signal x1 t, instead of x1 t I can simply also consider x1 t, all right. So, and for that the autocorrelation, for instance, instead of x2 t consider x of t, that is a single signal, we have a single signal. So, no need for the notation x1 x2. So, x of t, and for that the autocorrelation can also be denoted by r xx of tau. Instead of r11 of tau, you will also find this notation used for the autocorrelation, that is r xx of tau or r x of tau and so on, that is minus infinity to infinity. So, here we have x1 of t, x1 conjugate t of t. Here I simply have x of t, x conjugate t minus tau dt, and we have seen this is also equal to x t convolved with x conjugate of minus t. Further, if I take the Fourier transform of this, that is, remember the Fourier transform S S x x of f r x x, if I look at the Fourier transform of r x x tau, I can denote that by S x x of f, that is equal to integral minus infinity to infinity r x x of tau e to the power of minus j 2 pi f tau d tau, and we have shown that this is basically the Fourier transform. Remember, convolution in the time domain is multiplication of the frequency domain. So, this is x f f. In fact, this is convolution of x of tau with x conjugate of minus tau x f into the Fourier transform of x conjugate of minus tau, and we have shown Fourier transform of x conjugate of minus tau is nothing but x conjugate of f. So, therefore, this is magnitude S x x f square. So, what we have shown is we have shown this interesting result where S x x of f, or this Fourier transform, that is Fourier transform, this has a name which we will come to shortly. This is the Fourier transform of the Fourier transform of the autocorrelation S x x of f. The Fourier transform of r x x of tau is nothing but magnitude x f square, where x f is the Fourier transform of x of t. Okay, that is also important to keep in mind, where x f is Fourier transform of x of t, that is x of t and x f form a Fourier transform pair. Now, let us look at another interesting property of this Sxx of f. Now, look at this, we have Sxx f equals Fourier transform, that is, if you look at R xx tau, that has Fourier transform Sxx of f. Therefore, S or Srxx of tau is the inverse Fourier transform, is IFT, is the IFT of Sxx of f. All right, this is the inverse Fourier transform of Sx, which implies Rxx of tau can be expressed as integral minus infinity to infinity Sxx of f e power j 2 pi f tau d tau, correct. So, what we are saying is, since Sxx f is a Fourier transform of Rxx of tau, Rxx of tau is the inverse Fourier transform of Sxx of f. Now, let us evaluate Rxx tau at tau is equal to 0. So, Rxx tau, Rxx 0 is nothing but Rxx tau evaluated at tau equal to 0, which is nothing but this inverse Fourier transform Sxx of f e to the power of j 2 pi f tau d tau evaluated, correct. I am sorry, this has to be df, this is the inverse Fourier transform df evaluated at tau is equal to 0, and this has to be, now if you substitute tau equal to 0, what I get is minus infinity to infinity Sxx of f e to the power of j 2 pi f tau, tau equal to 0, this is 1 into 1 df, which is basically minus infinity to infinity integral of Sxx f df, which is basically, but remember Sxx of f is magnitude xf square. So, this is simply integral minus infinity to infinity magnitude xf square, and this is equal to R xx of 0. So, we have this relation, but now also realize that R xx tau equals integral minus infinity to infinity x t x conjugate t minus tau dt. Now, tau equal to 0, therefore, R xx of 0 equals, that is, now I have the autocorrelation expression for the autocorrelation, that is integral minus infinity to infinity x t into x conjugate t minus tau dt, integral from minus infinity to infinity, set tau equal to 0 in this, and what I have now, set tau equal to 0. So, what we are going to do is set tau equal to 0, R x x 0 equals minus infinity to infinity x t into x conjugate t, since tau equal to 0, which is nothing but basically, which is nothing but minus infinity to infinity magnitude x t square dt. Therefore, this is the, look at this, this is integral minus infinity to infinity magnitude x t square dt, which is nothing but the energy of the signal x t. Therefore, R x x 0 is the energy of the signal. So, therefore, R x x 0 is nothing but this represents the energy . And from here we have R x x 0 is basically integral minus infinity to infinity magnitude x f square df. So, from this result, let us call this result as 1 and let us call this result as 2. From 1 comma 2 we have, that is R x x 0 from results 1 comma 2 we have integral minus infinity to infinity magnitude x t square dt equals integral minus infinity to infinity magnitude x f square df, and this is nothing but this is the Parseval's relation. That is, if you take the total energy in the time domain, that is integral minus infinity to infinity magnitude x t square df, that is basically equal to minus infinity to infinity magnitude x f square df, that is the total energy of the spectrum, that is total energy of the time domain signal is equal to the total energy in the frequency domain. Alright, this is known as, this is the Parseval's relation. First this is known as the Parseval's relation, correct. Okay. So, this is your Parseval's relation for a continuous time signal. Or Parseval's theorem. For continuous time signal x t, correct. Now, what you can see is basically if you look at magnitude x f square, let us look at magnitude x f square. Okay, in the frequency domain, let us say this is your magnitude x f square. If you integrate this, correct, from minus infinity. So, this is your frequency axis. So, if you integrate this from minus infinity to infinity, we get the total energy, correct. So, the area under this from minus infinity to infinity, that is area under magnitude x f square, which is basically S x x f, right, from minus infinity to infinity gives us the total energy. So, this is magnitude x f square, which is S x x f. So, total energy integral minus infinity to infinity magnitude x f square df equals minus infinity to infinity S x f S x x f df. Okay. So, this is the total energy of the signal. All right. So, the total energy of the signal is given by the area under this S x x f, under this function S x x f from minus infinity to infinity. All right. So, that is integrated over the entire frequency band. All right. So, one can make the argument that is the energy corresponding to a band from minus w to w is therefore given by the integration of this function S x x f over that frequency band minus w to w. So, one can ask the question, what is the energy of the signal contained in this band from minus w to w? That is, if I look at this band, correct, and ask the question what is the energy, that is if I look at this band of bandwidth W and ask the question what is the total energy of the signal contained in this band what is the energy of the signal contained what is the energy of the signal contained in the band minus W to W, then that can be obtained by integrating this quantity Sxxf over the band minus W to W, alright. So, therefore, energy in band minus W to W, this is nothing but this is the integral of Sxxf over the band minus W to W. Therefore, what is this function Sxx giving? This Sxxf gives us what is the spread of the energy over the frequency domain, that is what is the spread, how is the energy of the signal xt distributed over the frequency axis or distributed in the frequency domain, alright. And if I am looking at a particular band, the energy of the signal xt corresponding to that band is therefore given by the integration of this quantity Sxxf over that band minus W to W. This is therefore known as the energy spectral density, right. This gives us the distribution of the energy in the frequency domain, correct, and therefore, if I want to look at the energy in a particular band, I have to integrate this energy spectral density or consider the area under this energy spectral density in that particular band minus W to W. So, this Sxx of f gives me energy, the energy spread or distribution of x of t in the frequency domain. This is therefore Sxx of f, which is therefore giving me the density of energy over the frequency axis. This is known as the energy spectral density. Sxx of f equals magnitude xx square. This is known as the energy spectral. So, this is known as the energy spectral density or the ESD. So, S, just let me write it clearly, Sxx of f is the energy this is the energy spectral density or the ESD. This is the energy spectral density of x of t, correct. It is giving the density of the energy of xt in the frequency domain. So, the density, correct, multiplied by the area or basically density multiplied by the length or basically compute the area under this density curve in the frequency domain pertaining to a band of interest, correct. That gives us the energy of the signal xt contained in that particular band of interest, alright. So, that is the interesting interpretation we have regarding the energy spectral density. So, this is a very important, and therefore, naturally if you integrate it over the entire frequency domain minus infinity to infinity, that gives us the total energy that is contained in the signal, that is integral minus infinity to infinity Sxxf df is the total energy contained in the signal, which is nothing but minus infinity to infinity magnitude xt square dt. Alright. So, this is the energy spectral density, and also observe another interesting property, this is magnitude xf square. So, naturally this is greater than or equal to 0, the energy spectral density is non-negative, this is greater than or equal to 0 for all f, this is magnitude xf square. So, this naturally has to be greater than or equal to 0 for all frequencies. Energy spectral density is a non-negative quantity, alright. Okay. So, this what we have is the autocorrelation Rxx of tau, alright, Rxx tau, which is a measure, all right, which is the measure of the degree of self similarity of the signal xt, that is Rxx tau. Take the Fourier transform of that gives us Sxx of f, which for which we now have a very interesting interpretation, that is the energy spectral density of x of t, and that characterizes how the energy of xt is spread in the various frequency band, is spread across the frequency axis in the frequency domain. Right. Let us now look at an example to understand this concept of autocorrelation and energy spectral density. Okay. So, let us look at an example to understand this, that is example of autocorrelation. Let us look at a simple example of the autocorrelation function. Let us consider this function, let us consider this function, or let us consider this signal x t equal to e power minus a t u t, where u t, as we are all familiar, is the unit step function, which is 1 for t greater than or equal to 0, 0 for t less than or equal to 0. This is known as the unit step, this is known as the unit step function, correct. This is 0 for t less than or equal to 0, correct, and for t greater than or equal to 0, this is 1. This is our unit step function, this is 0 and this is for t equal, this is basically 0 and this is the time axis, alright. Therefore, e to the power of minus a t u t, this is equal to e to the power of minus a t, t greater than or equal to 0, this is equal to 0 otherwise, correct, and therefore, this looks as follows. This looks as e power minus a t for t greater than or equal to 0, this is e power minus a t, and for t less than 0 it is obviously 0. So, this is basically your function e power minus a t into u t. Okay. This is basically your signal e power minus a t into u t. Now, let us compute the autocorrelation of this function. Let us compute the autocorrelation of the signal e power minus a t u t. Now, the autocorrelation is nothing but Rxx tau. Consider tau Rxx tau equals minus infinity to infinity x of t. Well, here the signal is a real signal, so no need for the conjugate. This is x t minus tau d tau. Now, let tau greater than or equal to, consider tau greater than or equal to 0. For this case, consider tau greater than or equal to 0. Now, if tau greater than 0 or tau is greater than or equal to 0, let us look at how the functions look. We have x t, which is e to the power of minus a t, correct, u t. We have x t minus tau, which is x t minus tau, which is, so this is your e to the power of minus t u t, this is your e to the power of minus u t e to the power of minus t minus tau u t minus tau, correct. So, this is shifted to t minus tau. Remember, x t minus tau is nothing but x t shifted or delayed by tau, if tau is greater than or equal to 0, and therefore if tau is greater than or equal to 0, it is delay, which means the signal is shifted to the right. Alright, so I have the signal xt, which is e to the power of minus t ut, and the shifted or delayed version, which is e to the power of minus t minus tau into u t minus tau. Alright, and now r1 rxx of tau is integral, well, it is integral minus infinity to infinity e to the power of minus t ut e to the power of minus t minus tau u ut minus tau d tau. Observe that this is non-zero only for t greater. Remember, look at this, if you look at this plot, the overlap is only after for t greater than or equal to tau. So, therefore, the product is non-zero only for t greater than or equal to tau, and therefore, I can write this as e to the power of minus infinity to infinity, correct, or e to the power of, I can simplify this as, since the product is non-zero only for t greater than or equal to tau, I can simplify this as tau to infinity e to the power of minus t e to the power of minus t, correct, e to the power of minus, I have e to the power of minus a t over here. So, this is e to the power of, let me just insert e to the power of minus a t over here, e to the power of minus a t, e to the power of minus a t minus tau. So, here I have e to the power of minus a t, e to the power of minus a t minus tau, the product is non-zero only for t greater than or equal to tau. So, this is e to the power of minus a t, e to the power of minus a t minus tau dt, and now I can simplify, I can remove e to the power of a tau, that is a constant, it comes out of the integration, integral tau to infinity e to the power of minus 2a t dt e to the power of minus 2a t dt, which is basically equal to e to the power of a t e to the power of minus 2a t by minus 2a integral from tau to infinity e to the power of a t e to the power of, substitute the limits, this becomes 1 minus, or this becomes at t equal to infinity, this is 0 minus e to the power of minus 2a tau divided by minus 2a, which is basically e to the power of minus a tau into 1 over 2a e to the power of minus 2a tau, which is equal to e to the 1 over 2a, which is basically equal to, or I am sorry, this is e to the power of a tau, e to the power of a tau. So, this will be, well, this will be 1 over 2a e to the power of minus a tau. So, this is your r. So, r x x of tau, if tau is greater than, so this is r x x of tau, but keep in mind this is only if tau is greater than or equal to 0. So, this is only if tau is greater than or equal to, if there is a caveat, if tau is greater than or equal to 0, r x x tau equals 1 over 2 a e to the power of minus a tau. So, alright. So, what we are doing in this is basically we are solving an example to compute the autocorrelation of this function e to the power of minus a t into u t. Alright. So, let us stop this module here, where we have looked at the autocorrelation, alright, the Fourier transform of the autocorrelation S x x of f, which we have interpreted as the energy spectral density, the distribution of energy of x t over the frequency domain, and now we are doing a simple example to compute the autocorrelation function. Let us stop here and continue in the subsequent module.